Yeah, hello Vedika, I'm audible.
Hello, sir.
Yeah, Vedika. Okay, so which chapter we have to start?
Work power energy.
Okay, do you have any notes for that chapter?
Sir?
Do you have notes for that chapter?
Yes, sir.
You can share your just.
The notes in the sense of like my own like notes.
Okay, like any reference from which I can take. Otherwise, if I'll write, it will take too much time covering that chapter.
Okay, so 1 second. I'll see.
Yeah, hello Advita, can you hear me now?
Yes.
Okay, so basically we can start another chapter. Alright, so the things we can discuss and cover the chap topics in this basically your work energy theorem, power energy, mechanical, conservative, non-conservative, vertical circular motion, power. If we cover this part, we are done with this chapter. In some textbook or some lectures, you will find that momentum part is also covered in this thing. But in some cases, the momentum is either covered in NLM or in this rigid body dynamics. Okay, okay, so I think here they have not covered this momentum part, or maybe in this part they might have discussed about this thing a little bit. So we'll discuss this part. Okay, so a simple idea. What is work? Work is nothing but how much useful force you had when you're moving, right? Assume this is the path. This some certain n number of forces are applied. Maybe this one, maybe this one, maybe this one. Okay, we are already well versed with the vector representation of the net force. So if I say this all force can be represented by a single force, let's say this is F, or
Okay.
let's say this is a representation of the net force on the net, right? F net. So we are very clear that this force is going one in this way, one in this way, one in this way. My body is moving in this direction, right? So which force is responsible for this movement? Understand the point? So what
Yes.
is work done? Work done is very simply. I'm not going in right now vector mod representation of it. I'm just going saying that work is basically whatever the distance you moved and which force have carried out the movement in that direction. If you multiply those two, you are going to get the work done. Okay?
Okay.
Now, if vector force is a vector quantity, right? It may have any direction. So which direction is going to represent the direction in the direction? Okay, which vector is going to represent in the direction of your x? So that we can actually get by using dot product. Okay, if you have f vector, if you have x vector, if we do the dot, what we generally get by doing the dot, it's like if you have f vector over here, if you have x vector over here, when you do the dot, you see what is the projection of f in the direction of x. Understood my point?
Yes, sir.
This is what you get. Or if you do another word, you can say what is the projection of x. This is this much, okay, on xf. This is what you generally get. So here when we are talking about f dot x, I wanted to say about this thing, okay, but when we write that, it contains both of the things. So it's all about
Yeah.
how the same. Okay, so I'll just remove it once. So yeah, let's go ahead. So if you see here what they have given, I think the yeah, this person has starting from here and ending up here, right? So he might be going in this way, the very, very small points, right? So what happens
Yeah.
if constant? When force is constant, if you take it any arbitrary point at this point, because person is supposed to move because the path is only given this, but force is on this point, right? So if you see at this particular point, if I resolve it into two parts, something this I'm going to get, right? So is it useful for me? No.
Okay.
In this case, this might be useful, but completely it's not useful, okay? Because look, it is only, for example, from here to here I'm going, right? Till here it is taking me upside, then from here to here it's taking me downside. This vertical force, right? After this slope, it is going to go downside. So what is the net upside force I need? Like out of the net force which is in the up direction, which is useful for me, only this displacement part, right?
Yes, sir.
Okay. So this basically is all about. You can look at this part. But the problem is we just had single F net, right? Here I don't have any force like this because they're saying if it's constant only in one direction. Look at this. F is in this direction. Particle wanted to move in this direction. So out of this, this resolution, this is the real force, right? So resolution will be on this basis. So it will be resolved in this direction and this direction. This is not useful right now. Okay. You are going in this direction. When you are coming downside, the force is still on this side. So this is useful. This is not useful. Understood?
Okay.
So that's how we have to think which part of the force is useful in my condition. Also, when we discuss about the forces, always remember what we are talking about. What we are talking work done by gravity, like work done by A or work done on the A. Okay,
Hmm.
these two terms are very important.
Okay.
You know that generally gravitational force is downside, right? So
Yeah.
when we write from the case here again, you know there's an object falling. Assume it is falling under the gravity. When I'm saying under the gravity, there's a force F is equals to mg. Assume in this influence it had covered some distance x, right? So if I ask what is the work done, now if I just ask you what is the work done, it's an ambiguous. What I'm even talking about, we don't know. We should know the context, okay? So I'm saying what is the work done by the gravity. So I'll simply say by the gravity, right? What is the force gravity has applied? Assume I'm saying this is the downside positive direction, okay? So in this case, I'm saying F have put downside force, and this H is also downside, so that's fine. This will result in FH. Understood?
Okay.
But in another word, say if I say what is the force on the gravity, that is negative. Understood? Because this is the work gravity has done. We have not done any work on the gravity.
Okay.
That's the thing. That's how we have to take it. In general,
All
if you have got F work on X or maybe some A, okay. If you have got work on A is equals to some X amount, so work by A will result you out minus X amount in most of the cases.
okay.
So these kind of thing we can actually have. What is the context of this problem? Okay, what I can feel is, and they might have kept it on this particular stage. There's a slope over here. At this particular point is this. So you are going to go in this direction. You will be covering basically H direction. So what is the path you are going to take? Instead of the slope, like either you may have moved this way, but you are going to move this way. So you have to
Okay.
calculate what is the net work you have to do in doing this. So again, idea is very simple. When you are at this particular slope, you are going in this way, right?
Yeah.
In this way, if you just resolve it, what is the force right now? If you see, mg is always downside, right?
Yeah.
So it has two components, one in this way, one in this way. This component is letting you, because if you see carefully, you are going on a curve path at some point, right? So
Yeah.
this force you can use is a small local centripetal kind of force. Understood? A local centripetal force. Because when you are curved, to stay at that curved direction, you need a little bit amount of the centripetal force. So here
Yeah.
is going to get used as a centripetal force or in that particular case. Otherwise, this force is responsible for your movement. So if this is the angle theta, what is this force? This is mg of cos of theta. Okay.
Hmm.
So what will happen is when you just if you just get it once, this is complete directions, right? So here you are having this, here you are having this, here you are having this, here you are having this. So if you see carefully, this is just a vector, right? So this plus this will result you this plus this result you this, right? So all these components will let you at the end of the day, very simple idea is the complete direction. They will let you complete direction mg a cos theta. Understood my point? It's kind of
Okay.
at the end of the day, what you are going to do, you are just going to do vector additions, very small points, right? For the path, if you just see carefully how much displacement you had at the end of the day. what is the path you have finally moved? This point and that point, right?
Yeah.
We generally say you have to get the net displacement. Understood? Net displacement. How you're going to get net displacement? You said, sir, I moved this point. Okay. So basically here to here one vector. From here to here another vector. What is it the net this much? From here to
Hmm.
here this much. So this is the net displacement you have to get. Okay. So at the end of the day, this only depends on initial and final point. We are not even
Yes, sir.
considering what path I have moved. Okay.
Yeah.
This path might be getting me more time or less time, but yes, the work is same. Okay. So this is one problem. You have tried this kind of problem earlier.
No, sir.
Okay, let's go with it. For this, first of all, we can simply remember the one formula. What is that? In this Poulet kind of system, the formula for the tension is 2 times of m1, m2, g by both sum of both. Okay, and acceleration formula is basically difference um, divided by this same thing.
Okay, sir.
This is directly we can remember. We are not going to derive it. So if we remember this thing, we don't need to drive things back. You are given like this condition is given fixed over the smooth pulley as given in the system. Both masses are also given. Find the work done by the string on the block of mass m. Okay. So basically, if you see these blocks are given, right? How you are going to calculate the this what I can say a work done due to this string? Do we have any ways to calculate work done by the string? Yeah, Dvika, do we have any ways to calculate the work done by the string?
Uh,
Look, if you see in a net way, this particular tension point, like this string, is applying force on this subtension T. So, you know, if this block is going to cover some distance x, at the same time, this block is going to go downside with x, and force on this will be upside, right? Yeah, Advika. Sorry, it's Vedic. Yeah, Vedika. Look, if
yes,
you
sir.
particular string, this point, the force applied by the string at this point is some tension T, right? We are very sure of it. At this point
Yeah.
again, the tension is C. But the context over here has been changed. Here, this block has moved up by this, and this block has moved downside by this, right?
Yeah.
So, what is the net force in this system? Could you remember? Could you relate it? What is the first, second? Wait. Okay, wait. They have asked. They have to check the distance in different time during the first second after the system is released from the rest. Yeah. The moment you have released, okay, the moment you have released the system, in the next 1 second we have to get the value of the this work done. Okay, so could you relate what is the work we are going to get in this case? Just think of it once. Look, most of the solution is already given. You just need to think: is it the complete solution or something is left? We need to do. I think.
So I guess that is only the answer.
What is the answer? Okay. So look, if you see carefully, whatever the work this string is going to do, this part of the string is going to do, this part of the string is going to do the same amount of work in a negative direction.
Okay.
Understood my point? If you could remember, there's a concept that work done. net work done by a tension or a string tension is zero. Understand? This is the main reason for that. Are you getting my point? Where I can make, yes, if you look at this someplace, I have empty. Okay, wait, I will just change. Yeah. What is the main thing about work done? The work done is very simple idea that this force and this. Here what happens is force and displacement. Okay, although I have taken different mass. Okay, this is smaller mass, so that's obvious thing. It will be going upside and this is going to go downside, right?
Yeah.
So force here is also upside and displacement is upside. So you know this work done is going to be positive, right? Here the force is upside, but the mass displacement is downside. X and T. This is also X and T. Magnitude is same, so it means this is W, this is minus W. You are going to it. Okay. So here the answer will come out as negative. Basically zero. The net answer is coming out to be zero.
Yeah.
Net individual points, if you see only this particular point, then answer is this. This particular point, the answer is minus 8j, but net comes out as zero. Clear?
Okay.
All right. So just look at this if you and let me know if you could understand something about this. Look, you're simply given a block having some mass kept over the platform is starting from rest, having constant acceleration upside. Wait. Start from rest with a constant acceleration. The block, I think, okay. I think platform has an acceleration of g by 2 upside as shown in the figure. You have to tell me what is the work done by normal forces. So basically, who is responsible for this object to go upside? Who is responsible for this?
The acceleration.
Yeah, the acceleration, right? Which acceleration it's going with?
G/2.
G by 2, right? So how we can actually interpret this thing? Look, earlier the thing is on the rest, right? Then later on you have provided some acceleration g. So if you look at this, if you just look at this small point, um, the object must be applying some mg, right? There's some n. So what is the net force on this? You know, net force is something.
N equal to mg.
This both thing results it to move upside with g by 2, right?
Yeah.
N minus
Mg
mg
equal to
m
mp.
g by 2, right? So this whole
Yeah.
thing results to 3g by 2. Can I say this?
Yes, sir.
So if you see here, this is what we have done, f dot x. So here we don't even need to dot because we know the direction of both force and displacement. So we have directly kept it. This is the displacement. Here it is half g by 2 t square. So this is also 1 by 4 and something. And it got the answer clear. Look at this. If you have doubt or something, you can let me know.
No, sir, I got it.
You got it. Okay. Now, hmm, all right. So basically, they are just saying, look, previously we were just discussing about the force which is going acting on a single direction, right? So if it is going in all three dimensions or two dimensions, we can resolve a single force into three components. Okay, we can solve each component separately, and we rest is history because we know how to solve the vector multiplication or integration for three dimensions, right? It's basically a
Yes, sir.
vector. So this is in x, y, and although at the end of the day, whatever the work you are going to do, that is going to be a scalar quantity. Understood?
Yeah.
That is going to, but previously in smaller steps you have to solve in a vector to vector forms. So this might be useful in this part, right? So you can see this is x and I, y and j. So you are doing some force in x direction in y direction. So that's how you are going to get this force. You can see this, you're going from 1 to something, y to something, and so on and so forth. Okay, right now in this, do they have given this question? Look, here they have given a very simple idea that you are moving in x direction with x force, right? What if I change the complete situation that force, force is given as minus y times of I plus x times of g. then what you are going to do?
So can you repeat once?
Look, in this case, they said your movement in I, okay,
Yeah,
had force in I with which is dependent upon x components, understood?
all right.
And for movement in Y, your force dependent upon Y component.
I
I,
component.
I have just reversed the thing.
Okay.
So in this case, how you are going to do? Look, a simple idea is assume you are going doing the same operation. I'm just taking this part and you can do for the actions, okay? So you will be doing f dot dx, right? So here for you're going to put x component. What is the x component? This is the x component, but its value is minus y. So minus y dot dx. I'll say with respect to this dx because I have to integrate it with respect to x. So for this guy is a constant, so it will stay same. So what is the integration we are going to get? Minus x. Understood?
Yes, sir.
And for this you are going to get something around xy. So the answer will come out 0. Why come out 0? He's saying I am applying, my movement is going in this direction, but force is applying on this direction. Okay,
Okay.
this is the context. X is saying my the force is in the direction of this, but it depends upon the upside values, a constant value. Okay, this will result you the net answer coming out to be 0 minus x
Yeah.
x. Okay, so let's come back to this. Look, most of the situations are same, so if you want, you can just look at this ones. We don't need to discuss much more further. Here you can see they have given a variable force, which is basically quadratic dependency force. So you just have to do f dot dx and simply just integrate and get the answer.
Okay.
There's nothing much more. Now we have come into another existence, that is graphical approach how to solve it. So basically, this is we generally do work is f dot dx. Whenever some
The
formula,
area under the curve.
yeah, basically whenever some formula is based on the multiplication of two things, then the area of that two things will result you the answer. If the formula, let's say the formula is like a by b, if the formula depends upon the division of them, then the this thing you can get by the slope of them. Understood?
Yes, sir.
Very simple. So work is basically multiplication of this. Means if I make a graph, okay, if I have a very random curve, so whatever the area it has covered, that is going to be your work. If some formula is there, let's say a and b, okay, and the relation coming out a by b, then the slope is going to give you the f. Clear? This is just a general interpretation. If anything is there having which depends on this, which is depending upon division of two things, okay, then you can get that particular thing by just making the slope, just by calculating the slope of that thing, okay, to those two directions. Yes. Okay. So here I think we cover. Yeah. Now you can see this part. Work done on a particle which is moved by a force scale. So you can see this is the force, right? X by this and this part, this by this part.
Yes, sir.
Constant. Okay, when the particle is taken from this particular point to this point along a circular path. So they have given us a path circular, so we just took out the two components out of it. This is just, I think this is X and Y, right? So basically you have got these two particular points also. So we may calculate the rest of the thing f dot dx. What even they're asking us to calculate? Mm, well, zero, right? And that's a very simple idea because particle is moving in this direction, force is getting applied in this direction. Are you getting a point?
Yes, sir.
Okay. So this force is only responsible in changing the direction. Okay, it is not providing any particular displacement because as per this force you are supposed to move in this direction, but instead you have moved in this direction. The force and the displacement is 90 degrees by themselves. So that makes no sense in this work done part. Clear?
Yes.
Okay, let's go back to this point. Alright, some important pointers. The net work done by action reaction pair can be positive, negative, or zero. But yeah, that is actually frame dependent. You can't see just by looking from one frame. Okay, ground frame may get the different value, and this frame can get the different value, maybe some A reference or something. Work done by tension, normal, and state on the tip is always zero, and frame independent. Yes, wherever you are sitting, this tension force is always going to be zero, or static friction and all. Work done by kinetic friction on system is always negative. Yes, that's also thing. Because look, when object is moving, we have an interpretation of the kinetic friction is that kinetic friction always applied on a moving object. Mean to say
Yes.
object is moving in this direction, then kinetic friction must be applied in the opposite direction. Right? So Fk dot x will result in negative. But in case of static friction, static is basically you have applied the friction, but static is only applied till this is in the rest, right? It has zero velocity. In that case, F dot x will come out zero because its
The
velocity is
displacement is zero.
displacement is getting out zero. Okay, because look, it is conservative force. Frictions are the conservative, so it won't be the case that if you have moved from here and come back to this point, the force is zero. The work done is zero. No, because it's a non-conservative. Sorry, it's a non-conservative force. Even though you complete a complete cycle, you go through a complete cycle, your force will have some particular value because these are non-conservative forces. Conservative be like, I'll only depend upon the path. Basically, end
So
of the
work is a conservative.
work done by something is conservative. For example, gravitational force. If you just take the example of gravitational force, right? These are a conservative forces. Understood? Mg and all, these are a conservative force. If you could remember, when I was going in this path, okay, work done by gravity only depends upon what is the real path I have covered. I just covered from top to bottom. That's it, nothing else. Because
Yes.
my focus was on the downside direction. I'm not dependent upon what is the path I have covered. Although in another way, I have covered each small path, right? This, then this, then this, then this, then this. But if I say, because this object is moving on this, if I say there is very small friction is applied on it, very small friction, okay? The friction is not that big to oppose the work which is going to done by this gravity, but yes, very small work you are going to do in this case. So you can say at this point, friction was like, let's say due to kinetic friction, right? You are applying force in previous direction, object move in this direction. When you reach here, force assume this slope. Friction applied this side, you move this direction. Friction applied this side, you move this direction. So you can see at each point it is giving some negative value, right? Which gets added up from here to here. Clear? So it is path
Okay.
dependent. It is not the start and end point dependent. Whereas other cases, if you could remember, that depends upon start and end the point. Clear?
Yeah.
Okay. Now we can discuss this problem once.
So if a particle is traveling in a circular path and it like reaches the same point again, then the work done will be zero.
Okay, wait, look at this. Yeah. So this is the case, right? In this circular path, an object is traveling. Okay. When there is acceleration is zero. I'm talking about when acceleration of the particle is zero. In this case, what will happen? Whatever the force is there, that is just to keep the thing into the direction. Your force is only doing one work. What is that work? Changing the direction. And changing the direction does not consider as a work. Understood my point?
Okay.
What you are actually doing, your object was facing this side, you applied some work and you made this object to face this direction. That's it, nothing else. Okay, this is what it is doing. If this was not here, what happened? The object would have moved in a straight, but due to this, instead of going in this way, it moved to this direction. Okay, it is still it followed this like for him with respect to him, he have moved in a straight path, but in general, his path has changed. He have changed his direction. Understood? This force is not helping him to move some small displacement. So that
Okay.
is okay. So in this case, the work done by this particular force, whatever the force is there, Fc, that is going to be zero. But if there's some external force Ft, tangential, then there will be some force. Okay, because it is
No,
going to
so
have
if the particle like comes back there, then work will be zero, right?
which case.
Like the particle starts from that point and like it completes one revolution and it goes back to the same point. So the work done will be zero.
Yeah, exactly. If the particle started from a and came back to again back to this particular point, the answer should be zero.
All right.
Okay. You can look for the this problem once. Yeah, options are given actually. So you can just read this problem once and let me know if you can actually assume, if you can read out these options and do a correct matching. Just let me know if you can do that.
Okay. So shouldn't option A be zero?
Mm, wait, AB0, work done by normal reaction acting on the block in this case. What is normal reaction acting? Which normal reaction we're talking about? We are given a mass m which is lying on the switch having mass
And
capital M.
what is the difference between option A and option B?
Work done by normal reaction, work done by normal reaction acting on the block and by the block. Yeah, there's a difference in this.
They'll
Look,
be in the opposite direction.
yeah, normal reaction is because mutual, right? Normal reaction is mutual in nature. So both are applying on this. Assume two objects are there. One is applying on this, one is applying on this. Okay, so on the block, this force, by the block, this force. Clear?
Yeah. So both of them should be zero, right?
Why they should be zero?
So because the displacement and the like the force are perpendicular.
Displacement and the force are perpendicular. Do the wedge are smooth or what case is given? Look, friction is absent everywhere, right? So what will
Yeah,
actually happen? Just look at this one. They have actually made look at this particular case. This is the wedge, right?
yeah.
This is N. This is the capital N. So what will happen? Ideally this can be resolved in two ways. If you see this block, basically this bigger, what I don't know what I should say this. Let's say bigger block and smaller block. This is going to apply N on this, and this smaller block is going to apply N on this in the downside direction. If you resolve it, this will result to N has one component and has some downside component. So due to this and N's this component, look, due to the this component of the normal reaction, this block is going to move in this direction. Understood my point?
Okay.
Look at this. Yes. That's why they have not asked what is the no, look, work done by the normal reaction is zero. Clear? Work done by the normal reaction is zero. Work done by So the normal reaction on block is not zero, or exerted by the block is not
So
zero.
why do we have to resolve it? Why can't we just take it? Why can't we just take the normal and like the displacement angle?
Look, because it is acting downside. Because the absence of the friction, if you resolve it, one goes downside, one goes in this way. Look, it is this line case. This is the point connected. At this point, there's two objects. Here it is applying N. This block is also applying N. Okay? Due to this, what happens is this pushed toward this side, this pushed toward this side. But the problem is they both are connected towards. They both are connected to each other. So this block is
Yeah.
also having this N this side, this N this side. So you can actually say they both have same N value. Understood? This horizontal force. But they are
Okay.
moving. You can say if you just look at the horizontal part, and
So
the
the wedge and the block are moving in opposite directions.
part is like n dot x plus this part is giving you minus n dot x. But there's a difference.
Okay.
This is okay. What is the difference? I think they are looking for the block, so this might be they are asking as a block, and this might be asking as a by the block. Okay. So if you look at this force on the block is moving in this direction, but force net normal direction is in this direction. So on the block, this is the negative part coming out, but by the block is applying force on this bigger wedge, right? So it is moving in this direction. So by the block, the work done is coming out at this much. Clear? This up
Okay.
down components don't have any consideration, even though they at the end of the day are making it to zero. This
Okay.
work done is also making at the end of the day zero, but the answer is coming out because
So how do you know which one is positive and which one is negative?
because of the motion. Look, normal direction is on, let's say this is a wedge, it is in normal directions, one component is in this direction. On the
Okay.
block, it is also in this direction, but the problem is they are connected and they are moving in this direction. Clear?
Okay.
So if you look at this, they both are in same component, same direction, positive. This and this motion is in opposite directions. This will result in negative. Magnitude is same, positive W, this is minus W. Results also is equal. Yeah.
So but isn't the block moving forward?
Which block moving forward?
The smaller block.
Look now, that is the frame. If you are sitting in the frame of this wedge, then you are going to say that this is moving downside. But
Yeah.
when this is going to go downside, look, net. If you just look at the net acceleration, that is a different. Okay,
Okay.
that is a different thing. And the motion of this block inside this thing is not due to this part. Is not due to this force. That is due to the gravitational force.
Hmm.
Yeah, it is moving this way due to the gravitational force. I'm
Okay.
asking what is the motion due to normal? Normal direction is something which is making them bound to each other.
Okay.
So that is what we are going to get to in this particular case. So at the end of the day, whatever the work you are going to do, that will result so you some change in kinetic energy. Understood
Okay,
that point?
sir. Yes, sir.
Okay. Yeah. So okay, this is spring force kind of thing basically. This is in case of spring forces. What is the work we have done in case of spring force? So in general, spring force is nothing but this thing. So when
Half
you have
kx square. Yeah.
this one to this two, so that will result you minus. Actually, force is like negative, so this whole thing should be negative. So this will result you x final square. Sorry, initial minus x final square. Okay, this is what you are going to get in case of spring. It's a simple idea.
Okay.
So let's again come back to the work energy. What it says is, in general, work energy theorem says all network. This concludes conservative plus non-conservative. Okay, all kind of forces acting on the system is just going to change your kinetic energy, nothing else. Clear? This is the interpretation of work energy theorem. So do they have taken any example? I really don't know what they have taken in this case. Okay, they are just simply saying there's an object. Uh, what we are doing. I think you might be applying some force F. This F is going to take you upside. So if you look at this condition, what's happening here? What is net forces acting on this object? So you can say, sir, there's a force F. This is going upside. Plus, there's a gravity on this force that is going downside. So mg downside. So because this is downside negative. Anything else I can't say. So these two will result in the change in kinetic energy. Okay, these two are going to change the result in kinetic energy. That's what
Okay.
we are doing. In general, we also know that this mg is a conservative force. Understood? Generally, these conservative forces helps in storing energy as a potential energy. Okay, stores
Okay.
energy as potential energy. Understood? So that's why when we write whatever the work you did, F should be equals to this change in kinetic energy. Uh, and this is going to go that side, right? So change in potential is something plus change in potential energy. So your final equations when you actually write it becomes initial kinetic energy. How you write kinetic energy initial? Because if I say that external net force is zero, so what do you get? Sorry, I'll use some more good ones. Look, what I did, all the conservative. Assume that there was two or three more conservative forces. Maybe spring was there, so spring case you can also add half x square something. Okay, more and more some conservative forces you have added. Spring force is also conservative force. Clear? All most of the
Okay.
natural forces, these are spring. These kind of natural forces are conservative in nature. Okay, so all these have kept us this. Now, if I say the net external forces, so you can actually say that this change in kinetic energy plus change in potentiality. How you can write this? This is basically K final minus K initial plus this is again
U
U final,
final.
sorry,
Yeah.
U final minus U initial. Isn't it we generally write when we say just apply the energy conservation, we say initial K final plus U
K
final
final plus U final
is
equal
equals
to
to
K.
K initial is it plus U initial. This is what we
Yes.
generally talk about when we say conservation of energy. That's it. Nothing much more to be discussed over here. So we look at this part. Particle having mass this much thrown vertically upward. Speed. Okay, initially you had given some speed. Okay, work done by the force of gravity during the time the particle was. Look at this carefully. They have not asked me the work done by the force with which I have sent it upside. They're asking force due to the gravity. A very simple interpretation is that this object is moving some upside. Okay, let's say the particle has covered some distance x. We are not going to get the real answer.
Okay.
Gravity is applying some force downside, right? So it doesn't matter how this thing has been changed. But if you look at this object started from here, went here as rest. What is the net displacement if I minus x? No, it's positive x because we are taking this direction as positive. Okay, this was force was downside, so you can take it as minus x. So what is the net answer? That is minus fx. Okay, clear?
No, sir.
This is one interpretation. This is one interpretation to be think of. Look, there's two ways to think this problem. What are those ways? Let's look at this. One way is this object must have started here, right? It will go top here. It will reach at the very top. Okay.
Yeah.
You can see that when you have thrown it with some speed, it is going to cover some distance. I know that gravity is all time working on this downside. But even though I can calculate this distance by using s is equals to ut plus half at square. Clear? Okay, let's not use this because at the end of the day I had to calculate time. I can calculate by using this way. I can yes because finally the speed is because particle during the time the particle goes up. It is going up, up, up. This is the moment. The moment its velocity goes zero, it will start moving downside. So I'm just talking about this distance, right? So here you can see you have u, you have a, you have two. You can calculate x, right? You can
Yeah.
calculate. Assume you have calculated something x in upside. So you can simply say mgx. This is one thing. If you see, this is the interpretation of potential energy stored. Understood my point?
Okay.
If I ask you how to write this in general term, you'll simply say, let's discuss what is the forces acting on it. I will say that work F net should be equals to change in kinetic energy. So right now, what is the work F net I have? I think I don't have any F external. Plus, what is mg? Mg is going downside, minus mg is equals to change in kinetic energy. Again, I don't have anything, so I have written it as mgx is equals to delta kx. That is what I am going to get. Can you see that change in kinetic energy equals to this thing itself? So they are asking
Okay.
me work done by the thing. So either I can calculate change in kinetic energy, or either I can calculate directly this thing. Understand the point?
Yes, sir.
So here the method they have used change in kinetic energy. Or other way you can simply if you know the x value you can use this. Clear? In this case, it's better to use change in kinetic energy. You don't need to calculate x. You can simply put the value because the rest of the thing is given to you.
Okay.
I hope this makes sense. Also, if you ask what is the final kinetic, because kinetic energy depends upon velocity. The moment you reach here, velocity becomes zero, k dot e becomes zero. So that is another interpretation. Clear? So you can see these are some problems. It's basically a different problem based on the integration part. Here, what they have given time dependent force F is equal to 60 zero act on a particle. If the particle I start from the rest, what is the work done by the force during first half of the thing? Okay. So how you can calculate it? Okay, what they have showing over here. Do they have given us the direction? I think no. Anything else? In the first, force is given, mass is given, displacement is given. In first 1 second, they are saying. Okay, so look here. You have two ways to solve this problem. One way is, okay, this force is positive. It is going to increase the particle's mass or something. So simple idea is that check out the initial kinetic energy and the final kinetic energy. But actually, the kinetic energy of the particle is changing by the time. Getting the point? Look, initially, okay, particle starting from rest of it. So initial velocity is zero, right? What is the acceleration?
Mm.
Acceleration will be coming out as 6t by m. So one way of calculating it, use this acceleration and calculate the velocity after time. Maybe what you can do? Yeah, after time 1 second. After time 1 second, what is the velocity of this particle? Okay, this is one thing you can do. So you know that yes, velocity is basically a 6t by m into t. Okay, use this and get the velocity after time t. So that will result to 6 by m because here the value is already given as 1 second. Okay? Initial velocity you already know that comes out as 0. So if you go and apply this thing, do you think you are going to get the answer?
Yes, sir.
Just think of it once. If you go this way, will you be getting the answer?
So it will just be half mv square, right? The
It
work
will just
done.
be half this way, right? That's fine.
Uh,
But try it once. I want
yes,
to
sir.
see whether you are going to get the answer or not.
Yes, sir.
You'll get right. Okay. So can you move to the next?
Yes, sir.
Okay. So let's come up to this part. Advika, look, what we can actually do is look. There's too many problems, right?
Yeah.
Uh, you can do one thing. You can give a try to all these problems. Okay. The
Okay.
problems which you are not able to solve or you are not able to understand, I'll explain in the next class. Is it fine?
Yes, sir. Fine.
This is it. Okay, so I'll directly move to the jump to the other. So the thing which I was discussing about conservative and non-conservative, right? So what is the conservative? Depend.
Which
It
is
is
independent.
very
Yeah.
simple. Starting and final. That's it. Work done in the closed loop is zero because Starting and endpoint become same. Potential energy is defined in conservate. This what is it? Defined in or can? I don't think this is can. It should be something else. Yeah, okay, that's fine. What I just told you that when we talk about conservative force, for example, mg and all, what is that spring force? So you have seen that when I was writing F external net F net, I said some F external plus mg. Then later on, I converted all these mg into another side take as a change in potentiality, right?
Yes, sir.
So when you have a conservative forces, what we can do is these can be stored as a this potential energy. Understood? If you look at this force always applies against. It is always like sorry. When you talk about frictional force, frictional kinetic friction always applies when body is moving this direction. It is applying this direction. But what happens is this just takes your energy and convert into some very other form which you are not able to convert back. Okay, understood my point? It is
Yes,
going
sir.
to eat up your energy and leave it. It is not converting it into some potential form. But when you look at this part, when object is moving upside, when it reaches here, what happens? All the energy gets stored in this in the form potential. It means if you leave your object, it will come back to its position. Here, but in this case, if object is moving here, friction was here. Assume the object reaches here and velocity becomes zero. It means it can't move further, and I don't have any acceleration. I don't have any external force law. What will happen? Because of zero potential energy, it don't have any potential energy. Whatever the energy was here, just was kinetic energy, and energy is getting lost. It is not getting converted into potential energy. Clear that point?
Yes, sir.
In this case, it is converting into potential. So you don't have to worry. Your kinetic is getting converted into potential. Potential into kinetic will happen. But here kinetic is not converting into potential. So very simple point. Work done in case of conservative is independent of path. Closed loop is zero, and potential energy is basically the is only defined for the conservative force. So this is what we are talking about. Clear? So if you talk about the conservative forces, gravitational force, electrostatic force, spring force, and centrifugal force. Clear?
Yes, sir.
And this basically meant that displacement in a closed loop. Where we can talk. Yeah, if you see, this is the thing I was talking about. If you could remember, I gave this equation to you.
Yeah.
Right? So one I directly gave you the previously. Here, if you just go and say this thing, you can see this, and this. All these things are telling you the answer is zero at the final stage.
Yes, sir.
Right? The answer is very simple because you are moving in some direction. Okay, and okay, you are going with displacement in one direction, but your force is applying in other direction. That results you providing a circular motion. Yeah, that is providing you a small point of circular motion. And you know when in circular motion you're starting from a point, ending up a point, so that will result your answer to be zero. Okay. Okay, look at this. Non-conservative. Potential energy is not defined. Work done is independent of the path and this thing. This can never be zero. Okay. Force like work done by this if this non-conservative force is there, if it is present, then its work done can never be zero because it is path dependent. It is like a distance. It is like a distance. Okay, if you have moved a little bit, it will never be zero. So I hope this makes sense. Bit of yes. Then again, we come up to the picture of potential energy. What is potential energy? It is negative of the work done by the conservative forces. Clear?
Okay.
Because look, this is work done. This is basically mg, right? Object mg. So when your work, look, if you see carefully, when I said the potential energy was stored in this object, when object is moved upside, upside mean to say who is the conservative force right now? That is mg. So when you did some this when this who is this person? Wait, yes, this is a conservative force. Conservative force have done some negative work. Only in that case you are going to get potential energy change positive. Change in potential energy positive mean to say, look, this positive mean to say you have increased your potential energies. How you are going to increase your potential energy? When some work is done against conservative force. Clear?
Yes, sir.
For example, if you look at this spring top, it is unstretched. You had an object, you pushed it, you stacked it like this. Even though you have kept it like this, but whatever the energy was there, you provide some velocity or something. Yeah, when you have made it like this, you did some work against this, right? It was applying force in this direction when you're trying to move inside the this spring was applying this force in this direction. What is that? What was that? Kx, right? You were pushing it against the spring force, against the conservative force. This gets stored as a potential energy. What is that? Half kx square. Clear?
Yes, sir.
So this is you can see actually at the end of the day. So that's why we generally write work external as delta k then delta this. So this is the interpretation at the end of the day when kinetic energy is changed to zero, you get this thing on this. Yeah, these are some small examples. I don't think it's that important. Hmm. Okay, let's do one thing. You have two problems which you can discuss. Either this one, either this one. Okay, Advika, which problem you wanted to get discussed?
So the first one.
Okay, the first one. Yeah, so look at this. You are given a uniform cable, have some mass m, and length is also given as L, right? Which is placed on a horizontal surface by 1 by nth part is hanging outside. So this is 1 by n. So basically below the surface to lift the hanging part of the cable upward should be the work you need to do. So again, look at this. Do I really have to bother about this part?
No, sir.
Should I really bother about only this part? I think so. Yes, because look, when I'm going to pull it, I'm only going to pull this much part. Can I say this?
Yeah.
So can I say when you look at the end of the day, this surface is like this. I need to maintain some velocity? Do I need to maintain some velocity over here?
Uh,
No, I don't need, right?
so I did
Just
not understand what you're trying to.
just a second. A lot of insects on my left. Okay, I'm just saying when you are going to take this object to this up, I just need to keep it from here. All these points. This assume 3 points are there. I just need to keep all these points from here to here, right? Nothing
Yes,
else.
sir.
So for this, what you can actually do is, I just wanted to change its kinetic energy. Like if this part has some kinetic energy, this has some. I wanted to keep all this kinetic potential energy. Sorry, I wanted to change its potential energy from some value to zero. Now you will say, sir, why zero? Because look, it's up to you what you wanted to say. You can, if you say this is zero, this will become a positive potential. This is higher, this is higher, and this will be much higher. Understood? If you say
Okay.
this is zero level, this will be minus one. This is going to be minus
Yeah.
two. Going to be minus. Here's something this you can actually think of.
Yes, sir.
Okay. So here what we are doing is we are going to convert the potential energy of each point to zero finally. If I do this, I'll have all the points at the table. That's it what I want to do. So if you because you have not you don't we have not understood the part of your what is that? Yeah, sorry. We right now we don't know the concept of mm, center of mass. Okay. In case of center of mass, if some hanging rod is lying, what happens? Their net potential energy lies at the center part. Okay. If we don't know this, how we can solve it? We can simply calculate the uh, what is that? Change in your potential energy. How you can do this? You know the total length hanging this part is L by N, right? Can I say this?
Yes, sir.
Okay. So what is the potential energy net? If I say I'll go to some distance x, I'll get a small part dx, right? So what is the potential energy of that object? That is, I am at the zero distance. Okay, I'm at the zero right now. So I'm going downside with h. So what is the potential energy I'm going to have? Minus h, because this direction is negative for me. So the potential energy dx, what is that? Um, I think dm dot x. This is what I have right now. What is dm? Very small mass of the total length, right? So total mass of the object was m. Total mass of this table, okay? M by L
Okay.
is equals to dm by dx. Can I say this?
Yes, sir.
Okay,
So, but for DM, don't we just need like DM by N?
dn by m.
Like whatever the part is hanging, don't we just need that mass?
Yeah. So that we are going to take dependency on just L part, okay?
Okay.
X part. So just a second. You can just look at this one. So you would get dm is equals to m by L times of dx. I just wanted to get this smaller distance, okay? Mass of this smaller part. So now you can say if you just replace it, you are going to get ml x. Oh, sorry, x is also there dx. Okay, this is what you are going to. So when you integrate it, from where to where you have to integrate, you have to integrate it from okay, zero, just zero length to minus L by n. This length is L by n, right? So negative L by n. If you do this, what you are going to get? M by L will as it is. It will become x square by 2. So this gives you answer as, also g is also there, sorry, because we are putting the part of the energy, okay? So g is also there. We'll just keep it as here. It will become m by L. This x square is what? When you keep it once zero, the answer will be becoming negative. Here you are going to get, sorry, this is m by L. What is this x square? L square by n square and 2 square. So L will get cancelled. M L, sorry, ml by n square g and g. This is the answer you are going to get. You can see this answer.
Okay, sir.
Clear? So this is how you are supposed to solve these kind of problems. Just integrate it. Now look, conservative force and potential energy. So this is the relation we are going to do. F, yeah, that's actually the relation we are going to do. Nothing else. Because when you have some conservative force, okay, potential is actually only you are going to store when you are doing some force against it. Okay, if you are doing if work has been done in the direction of force, potential energy will decrease. So if this force is positive, this is going to be the whole, this is going to be negative. This change in potential is going to be negative to make the force path positive. Okay? So direction, it's this, what I can say, the sign convention of both are going to get reversed by each other. We can actually look at some example if we have, we don't have. Mm, okay, if you take this as a U, you have three different components. You have to solve each of them one by one. Okay, and when you add it, the force you are going to get this in each of them direction. Let's not discuss about this here. Let's, if you see, this is an equilibrium point. Okay, when you pull lift this pull leave this object at this point, it will come back to this position. You can see
Yes.
by hook, hit and try, you can maintain the body here also. You can maintain the body here also. But the difference is, first of all, from here, if you take it at this point, what will happen? The object will come back. If
Yeah.
you take it, it will come back. But if you take it here, what will happen? It will directly go back. It will never be reached back. So what happens? This is stable. This is equilibrium. This is equilibrium. But this is unstable. This is stable. And if, what about this point? This is neutral. This is not. This is none. Like what I can say. This is not even a. This is not an equilibrium point. Okay? If you leave it here, it will move down. So this is not a point of equilibrium. It's a neutral point. Clear? So why we are talking about this? If you see at this point, the force is minimum. Understand my point? Sorry. At this point, potential energy is a minimum. The point of minimum potential energy is equilibrium. Equilibrium, yeah, that is a stable equilibrium. Okay, minimum potential energy point. Any object has some minimum potential energy point. In that case, you can say like that also depends upon the forces. So in this case, this is the point of minimum energy. Clear?
Yes, sir.
Okay. Advika, look, this till this I think this is fine for today's discussion. I will try to go with the rest of discussion in the next day. Is it fine?
Yes, sir.
Look, so far what we can do, if you could remember, we have skipped many problems in between, right? So try
Yes,
it
I'll
once.
try all of them.
So yeah, Advika, that's all for today's session. Uh, you can just try rest of the problems which we have skipped, like these kind of problems. I think we have not
Okay.
discussed. Yeah. So yeah, Advika, that's all for today's session. Goodbye.
Okay, sir. Thank you, sir.